Good afternoon, everybody. My name is Chris Kozirakis from Stanford University, and it's a great pleasure and honor to introduce Nafea Bshara for the last keynote speech of the conference. Nafea is a VP and a distinguished engineer at AWS, where he leads the strategy and architecture for AWS custom chips. To be honest, Nafea's career represents ASPLOS' architecture support for programming language and operating systems better than anybody I can think in our industry. His Nitro design, the design that his startup at Annapurna Lab put together, and then it was acquired into AWS a few years later, established why custom chips can play a significant role in drastically improving performance, I/O efficiency, security, and management of cloud infrastructure. Pretty much every cloud provider that I know has cloned his design in the subsequent years. The Nitro design also made it much, much easier to introduce various architecture data center without complicating management or security in any way. Nafea and his team built on that to be the first to massively deploy ARM CPU chips specialized for cloud efficiency. This is something that our community has been investigating for probably a couple of decades before it actually happened. Nafea has also worked on using custom hardware to improve networking and storage at cloud scale. Today, he's going to talk to us about how to build end-to-end infrastructure for ML, including the chips, the compilers, and networking that are necessary to get AI to work at the scale that we all expect it to. So please join me in extending a warm welcome to Nafea.
Thank you. And before I introduce myself, I want to introduce Yida. Yida Wang runs our research for Trainium. We cannot miss him. He's the only one with the AWS hat. So if you have any other questions, okay. Everybody can hear me in the back? No? No. That is rare. How about now? Works? Works? Okay. Again, Yida, he runs our research with AWS hat. If you want to have looking more for research work or some summer internship, please reach out to him. Today, I'm going to talk with you about if ASPLOS had a Disney World, it would be Annapurna Labs. And I'm going to show you what that means, for what you can do when you can have all the tools to innovate at AWS scale and build all these custom architectures to service the software and the operating systems. So just a quick intro. Annapurna Labs, I started one of the co-founders of Annapurna Labs. We started to do custom silicon for infrastructure back in the 2011, 12. Amazon Cloud was our first customer, and then they liked what they saw from us to acquire the company. And again, they created Disneyland for us to innovate. In that Disneyland, the first product we built, a product called Nitro, which is today people call it SmartNIC or DPUs. When we created it, there was no such thing. But it's a device that sits in the servers today that offloads what is today called SDN and SDS and security and hypervisors and RDMA, even replaces TCP. Transport protocol. After we delivered a few generations of Nitro, we also went ahead and built custom servers, replacing our AMD and Intel. Right now, it's probably the most used servers on AWS Cloud. 98 of our 100 top customers are using majority of their production workloads on this. We did this when nobody thought we could build the product that can replace x86. But again, if you think about operating systems and programming language and give them the right attentions, you can build architecture that can replace incumbent products. The third product we introduced called the Trainium and Inferentia. as the name still, inferentia for inference, Trainium for training. Not going to complicate it, calling it Ice Lake, Sapphire, Hopper. It's very simple. Trainium and Inferentia 2 and Trainium 3. So you guys know which one. And Trainium 3 comes after Trainium 2. So, but that's nice. We can laugh about it, but it's not a joke. One of the biggest objectives for us as engineers and scientists, we need to minimize the mental overload on our customers. You introducing something new, make it easy for others to use, even to remember the name. Okay. Now, I mentioned those 3 product lines. We have at least 12 chips in production, and these are not small chips. So anybody who were seeing chips, these are some of the largest chips ever built. Each one of the chips you see here ships millions, if not tens of millions, at scale. So we're not talking about ideas and theories, and maybe we're shipping at scale, which puts us probably as the largest chip company you never heard about. We are in the top 10 largest chip companies in the world, giving the scale and giving all the products we have. Okay. Why we build custom hardware? Once you go to the cloud, you start working with 3 to 4 to 5 million customers. You learn so much about what the customer need, where the market going. And we found ourselves that we cannot innovate as fast as our chip suppliers provide. We had to innovate faster, and what we call shift left. So that was the main motivation to bring something newer, faster to our customers. Also, because we operate the whole thing, the software, the hypervisor, the protocol stack, the data center, the cooling, the electricity, we can drive efficiency across the board, either cost, power, or any other type of efficiency you can have in mind. We raised the bar on security. And since you own the whole thing, the chips and the rest of the data center can work together to increase the availability and reliability for products. Some of the products that you come to join, we commit on paper to make them 9 nines or 11 nines, 99.99999% durable or available. So to do that, get to that level, you cannot miss anything in the stack. Okay. When we design our chips, again, luckily we have 3 million customers. You easily can avoid the temptation of focusing on one use case and one application. Like in today's world, everybody says, I can build a much better product for inference for transformers. But who said that in 2 years, transformers is going to be the killer application? Okay, the market changed so much. When we started building our own Trainium, remember Trainium is the product for ML. In 2016, 17, and I was in conferences like this, on a survey, roughly 70 to 80% of the people would have told us that convolutional network and int8 will be all you need. And that's the worst, as an architect, as system people, that's the worst thing you can do. You think you know what the end use and where the industry going to be 2, 3, 4 years down the road. So when you will build products, and all our products that you saw before, we designed them for have generality, programmability, because things are evolving so fast, thanks to ideas from folks like you and others. Even though it may cost you a little bit more in the chip area, or cost you a little bit more in the schedule of the project. The framework we think about when we talk about programmability and cost, we try to minimize the cost of mistake. That's the framework we're thinking about. Minimize the cost of mistake, because if you build a product that is limited in any vector, performance, programmability, scale, especially in the silicon, and you miss the market, you missed by 2 years. That's a very expensive cost. I rather pay 5% more per the chip than miss 2 years from the market. So programmability is another key piece. Scalability and reliability, and how easy for users to use. In many times, and I'll show you that today during when I start deep dive into the products. you could be tempted to build products that have the utmost efficiency or utmost performance. For us, the more important piece before utmost performance or utmost efficiency, it have to be the utmost usability and the easiest mental burden on the user to adopt your technology. So I keep telling my team, our products, our number one feature, they have to be boring to use. If the user have to go read the docs, we already lost half the users. Okay? And that's a hard discipline, because you can always be tempted to say, I can do this extra feature that make it 10 times faster, but it's hard to use. So boring, and you know, you can always have fun with idea, but the biggest fun is when you have users using and telling you how good the product is, not how nice your paper was or how cool your idea is. Having users using products at scale is much more satisfactory than giving you good feedback on a smart idea. And to do that, you have to get the product easy to use. So you'll see that through the rest of the slides. Okay. So until now, I gave a generic overview of what we do in Annapurna and the design principles. I'm now going to go a deep dive into how we design our DSA, domain-specific architecture for machine learning workloads. So I'm sure this is a bit boring for a lot of you guys here, but what is DSA for ML need to do? Is a product that is really heavily focused on linear algebra. Math mult is probably 90% of your power and time doing math multiplication, some vectors. It's a product going for ML. You have to build a product that has a flexibility in designing the nonlinear math functions. Sometimes sigmoid, sometimes you're going to turn edge, sometimes you're going to do a reload. There's a lot of innovation happening outside the matrix multiplication, because there's not much you can improve in matrix multiplication or innovate. Okay. The data types are changing. People do start with 32-bit. Now people can say, oh, maybe I can do 4-bit, maybe I can do ternary bit. So any DSA targeted ML have to have flexibility on the data type. You also have to have flexibility of how you do the distributed training. Even up till now, people haven't figured out what is the most optimal algorithm to get distributed training at scale to be efficient. Also have to think about that as cost blooms and the models grow, you have to be aware that there's other techniques to reduce computational or memory or network, like sparsity, compression, quantization techniques where you get smaller bits. When you combine all of that, those are the unique things that makes a specific DSA optimized for ML. And another thing you need to do when you design a product for ML, giving the past experience, you have to make sure you have unbound in scale. The model can be bigger. You have customers who want to do larger training speed, so you need to scale the network and the clusters to do training faster. Or you may have customers who want to do lowest possible latency, so you need to find a way to make the algorithms and the hardware to give you possibly lower latency with different techniques. Okay, I know it's not common to ask questions in these conferences, but I don't mind. If you have any, raise your question. You raise your hand, ask the question. I repeat it and I answer. Okay. So Trainium, let me walk you through a little bit of the Trainium stack. And as I said, we're in Disneyland, so we have a ride for each one of them. We have a team working on each layer of the stack, and we innovate across the stack. And most of the time, they are in the same building, or maybe just 2 floors above each other. So it's a lot of collaborative work in the developing Trainium. It's a lot of fun. And I'm going to walk you through all the layers step by step. The first one is the chip itself, then how you build the scale-up network and the collective that use the network, the compiler, and how that compiler fits with the frameworks that we have today. Okay, so giddy up, let's dive deep. This is one of our first chips And I'm going to start using the pointer and hope it works. Yes. Okay. You see, in a typical chip, there are cores. And if you notice in this slide, I'm going to go over it, there are only two big cores. Two big cores, data movement, memory, and few compute engines. The biggest and most important is what we call the tensor engine. It's a systolic array. Why systolic array? I'm going to walk you through it because the most power and memory efficient for math multiplication. Then we have other programmable engines for vectors, for scalars, some C programmable engine for other people to use, and a big cache. And I'm going to go dive into each one of them. But roughly, if you think about it this way, it's not like GPUs. Maybe the external interfaces are like GPUs, but here you have two big cores, or X number of big cores, instead of thousands of threads. And that's going to drive a lot of the architecture efficiency and the differences. So the first question I get asked, okay, how is this different than GPUs? And my first answer, let's talk about how it's not different than GPUs. It's not different than GPUs in the sense the Trainiums and let's say the Blackwells are using the same latest TSMC processes, the same latest, fastest memory we call HBM. They're both using the largest package available, chip package. They both use dual dies, two dual very big dies connected to each other with a special interconnect. Okay, they both integrate with the ML almost in a similar way, ML frameworks. They both have RDMA to scale to go multi-node and training. And inside the server or inside the rack, they both have a similar memory mapped network for scale up. In GPU space, probably called NVLink, we have something called Neural Link. So a lot of familiarity. Going back to the first design principle, it has to be boring. It has to be similar as much as possible from an end user point of view. You know, how you build a network, how you train, how you distribute the loads. They have to be as similar as possible. And that's where the similarity are. Let's talk about where the difference. The main difference, and I talked about the previous slides, we have few very, very big cores versus thousands of threads. Okay. One of the benefits of our having big core, why we went with big cores, because each core is a big systolic array. And in the DSA for ML, you should know at least 85% of the compute and the power of the device is going to end up going on the matrix multiplication. And that matrix multiplication, the most efficient way to do it is in a systolic array. Okay. I will not be able to do computer graphics, but I'm building DSA for ML, and ML by definition is a very large linear algebra job. Another thing, because we have few cores, and the core is doing huge math multiplication, there's less overhead, less gates, less power wasted on control and managing threads and synchronizing threads and optimizing threads access to shared cache and shared memory. Okay. It's also, you know, you have 2 or 4 or 8 cores accessing the system. There's not a lot of randomness. You know what's going on. Versus when you have 4,000 threads, it's a lot of randomness, a lot of things stepping on each other, a lot of sensitivity to one being stalled and stalling the others. So there's, again, a much bigger advantage to have big cores. Another piece we have is what we call dedicated engine, a collective engine. Collectives is I'm going to go into details later about it, but it's the thing that does the basic summation and averaging when you sharing information between accelerators or between GPUs. In the GPU case, those functionalities of averaging and sharing and adding stuff that goes between GPUs are done on the same cores that doing the computation. In our case, we have dedicated, so we can have more chances of pipelining and hiding latency. Okay. Now, how are we different? So I talked how we are different than CPUs. How are we different than classic CPUs, not GPUs, C with the C. And a lot of you guys studied CPUs. I'm sure everybody here did computer architecture. And you learned about, pipelining and out of order and caching and TLBs and a lot of things done in hardware. And people did PhDs and spent 40 years building that. And then we leave some stuff to the compiler, like fusing and code placement and loop unrolling and vectorization. In the ML DSA we built, Trainium, we made everything in the compiler. Really did not want to spend a single cycle, a single gate in the hardware trying to do caching, software caching, predict what's the right algorithm, do the hazard checks. Since the same workload you're going to run is well known upfront because it's an ML network, because since you may likely to run on tens of thousands of GPU, the same code for hundreds of days, if not thousands of days, it's better to take all your time in software, in the compiler, to squeeze every 0.1% of that load, instead of baking things in hardware, like what is your cache algorithm, because when you don't know even how the code is going to change the next 3 years. So we leave everything as much to the compiler. Now the trick, of course, how to make the compiler simpler, and I don't get to that. But a lot of the stuff you learn in the computer architecture class, all the techniques people build to build CPUs, throw it away. Not relevant for us. What also throw away is that RISC is the best architecture in the world. For this use case, actually, we went after very big heterogeneous CISC cores, not RISC, CISC cores. And I hope I'm not insulting anybody or offending you guys by saying we're going back to CISC world. That's what the hardware is. The hardware is a very big CISC cores with some synchronization parameters. I'll talk with you about it. And not less important, dedicated hardware for tracing and debug that is non-intrusive. You don't need to change the code, or you don't need to slow down the machine to get a cycle accurate tracing or debug. And the compiler is the one that does the lowering, tiling, vectorization. I'm sure you heard a lot about these compilers today. Fusing, memory allocation is done in the compiler. Cache management is done in the compiler. So load from the cache, store from the cache, look at the cache place where everything gets placed. It's all done in the compiler. So everything you learned about LRUs and N-way caching, we don't need any of that. The compiler takes care of it ahead of time. Even reordering, pipelining, hazard checks, read after write, write after write, the compiler can easily take care of it. And we just need to give it a little bit hints in the hardware to make it optimal from a performance point of view. So why we did it CISC? First of all, typically, we work on so much big data that each instruction is about 512 to 1,000 cycles. You can afford having CISC for these big instructions, okay? And by the way, less than 20 different instruction types consume 99% of the cycles. Also, on the instruction side versus data side, usually the instruction is like 1 out of 10,000, 1 of 100,000 versus the data size. Because one instruction says math mult on this tensor, or 3x3 convolution with padding on this tensor, where the input is FP16 and the convolution is integer 8, and I want the output to be also FP16. This is how complex these CISC instructions are. But it's okay, you can afford having those complex instructions when the data size you're working on is so big. Okay, so the ISA, as just mentioned, the ISA is, we enrich the ISA to make it aware of all the data types coming in, coming out. Otherwise, we'll have to add another set of ISAs for translating the data types or changing the convolution or padding or not padding. I don't want to add extra instruction for each one of these. In many ways, remember we said we punted most of the work to the compiler? One of the ways to keep the compiler simple is giving the compilers more complex CISC instruction to work with. The compiler have less instruction space to work on. And much more cleaner mapping between the compute graph and the ISA on the hardware when the instructions are CISC based. Okay. So when you go after CISC architecture and unknown future, and you need design for programmability, one of the things we did is that the data path, of course, you build all the data with all ALUs and all the data types and all the conversions and all the rounding modes and all the access pattern to the memory, row major or column major, you name it. But the instructions are implemented in the CISC instructions are implemented in microcode. So back to our Disneyland, imagine you're out of college and someone came up with a new ML model. That ML model, to optimize it, you need to create a new instruction. We have students that are 2 weeks out of college implementing instructions, shipping it in the compiler, and 2 weeks after, people are using it and deploying it because the instructions themselves are implemented in the microcode. And you can add them without complicating the compiler too much. Okay. Now, what if we need a new instruction that actual data path doesn't really support, and you want to write it in C, and maybe there's some weird math that we forgot to bake into our hardware. We give you a standard cores with 1,000-bit vector engines and tens of those cores. You can write a program, basically it's a programmable SIMD engine. We call it GP-CMD, general purpose SIMD engines, to write that user code that we did not, for things we did not think about in baking into the data path. Okay. Now I explained the instruction, explained the CISC, I explained how we do write micro ops to program the instructions. Now, how do you stream instruction into the chip and how you schedule them? One of the most common mistakes when people think about data flow or systolic arrays is, oh, everything's programmed, data flows from this, weights flow from this, you read from SRAMs, cycles are accurate, you can schedule everything, cycle accurate. There actually is 3 or 4 startups in the world that build chips assuming you can schedule everything and cycle accurate, and they come tell you this is the lowest latency system. The reality is, when you're using external memory, you cannot control timing of the memory because memory have refresh, there's conflicts, there are back addresses. You want to try to reorder access to memory to get better performance. You're using network. You're adding jitter and latency to the system. You're using dynamic controls. With all of this being added, you cannot assume you have cycle accurate scheduling. On the other hand, you cannot assume the worst case scenario and start adding knobs. Is this transaction maximum going to take, let's say the matrix multiplication maximum going to take 5,000 cycles, but typically going to take 3,000 cycles. And I'm not going to let the vector engine start working until the matrix finishes. And the matrix, if it's going to take 5,000 cycles, I'm going to have the vector engine wait. So what we did is we allowed each one of those engines have their own independent streams with very simple handshakes. So when we write an instruction, it says, this is a vector instruction, but don't start executing until that matrix instruction finished, or don't start executing until 300 cycles before because we allow fine-grain overlapping between instructions. That's what I call fine-grain granularity in hardware. The compiler knows about it, but the compiler also knows that it doesn't know the exact timing, so we put the primitives in hardware for scheduling. Okay, that was instruction. So let me talk a little bit about data movement. In data movement, Christos, I have the 20-minute, right? Okay. So in the data movement, remember I mentioned if you're running GPUs, thousands of threads, or CPUs, you're reading cache lines, 64 bytes or 128 bytes. And then a lot of things are overlapping. And then from a cache point of view and the DRAM point of view, it's all random access. You can do as much as you can to improve efficiency with random access, but you cannot really get the max efficiency. We chose to use very large, big CISC cores, and each instruction go reads tens of hundreds, even mega or kilobytes, sometimes megabytes. Then if the data movement is so big, you can structure it when it accesses the cache and accesses the memory that you can have maximum utilization. Okay, so even if we and the GPU, let's say, use the same memory, likely we get 15–20% more efficiency from reading from that memory versus a typical GPU. I'm going to skip over this. We support all the data types. The most interesting one is actually the configurable float, 8-bit float, where you can do change them. Go ahead. You have a question here. So your question, sorry, excuse me. Sparse data. Okay. So the question is, if you have large data movement, how do you handle sparse data? Here's the good thing. Because you have CISC and because you have large data movements, you can bake into those data movements and instructions various patterns, including sparsity. Structure sparsity, block sparsity, compressed sparsity, different data types. You can express that. You can express that in the CISC command and bake it in. Okay. By the way, it's the same problem you also have if you're doing small data movements. But here, because we can, instructions are more rich, we can express that even more easily. Okay. I'm going to skip the rich data types. I'm still halfway through. Another interesting we did, for example, when you're doing training, usually you have some base weights and you do the back prop and you do the small delta to fix the error, to update the weight. And usually the weight is big and the error is small. Now, for sake of example here, I'm just giving a very simple example. If you have a weight of 1 and you have a gradient of 0, you add them. We went all to same elementary school. They teach you 1 + 0, 2. You round it down, you go 1. 100% all the time. Now, if you're adding all of these, like you say, you're doing gradient updates thousands of times, and each time you round down, you're adding so many of them, and you're still down to 1. And this caused a lot of problems with conversions, and the only solution to do it is go increase your data type. Instead of using 8-bit, you have to use 16. Instead of 16-bit, you have to use 32. And it's end up making memory movement double, network double, the computational power double. What we did in our Trainium from early on, we did something called stochastic rounding. And with stochastic rounding, if you're adding 0.2, then 80% of the chance we round it down to 1, and 20% up to 2. And I know a lot of people wrote about it. There's a lot of papers about it. But back to us being the Disneyland, we see something we put it in the hardware. Because for us, by the way, gates are asymptotically free. Right. Sorry? There's a question. If you do stochastic rounding, does it mean training stochastic, undeterministic? Excellent question. And for naive people, we're going to make this completely undeterministic and totally nightmare. In our architecture, all the devices get seeded the same seed, and all the stochastic rounding comes from the same polynomial with the same seed. More than that, every epoch, every training piece, we reseed, so make sure they're always synchronized all the time. Okay? And that's how you can reproduce. If there's a problem, you want to go back, you want to reproduce, you reseed it. Good question. Okay. You guys believe me, it works and it's better than everything. I'm going to skip this. Okay. Okay, so here's another thing where I'm compressing an hour talk into 2 seconds. You have few chips. No model today fits in one chip. No model fits in one rack. You have to do multiple racks. Then a lot of smart people came with a lot of concepts called distributed training. In papers, we say call it data parallelism and model parallelism. And inside the model parallelism, people do pipeline. There's tensors, a lot of paper around it. I think the actual models, the actual concepts is less of an important. What's important to know is we call this 3D parallelism. We shard weights and data and different ways to the same tensor or different layers of the stack on different ways. We call that 3D parallelism. And 3D parallelism is by itself is a very big challenge. But the biggest challenge in our world is to get compiler folks to understand that 3D parallelism is something the compiler have to think about from day one. And we've almost every compiler has been built in ML, built in the concept of I'm optimizing for a core and not I'm optimizing for a cluster. And if the distributed 3D parallelism is an afterthought, it's hard. It's hard to get instructions and data movement to get overlap or parallelized or fine-grained pipelining. Okay? Now, to do 3D parallelism, you need to, depends on which type of 3D parallelism you're doing and at which stage. Sometimes you have to move very, very small bytes very quickly, and that's the latency-dominated problem. Sometimes you have to move a lot of data, then become a bandwidth-dominated problem. And when you're doing all of this, every techniques in the box, how to make network faster, you end up implementing in the Disneyland we have. We do multi-rail, so you do a lot of parallel design, you do zero copies, you do in-band serialization, you don't have to go through a CPU or some general orchestrator to tell you when the job is done because data moving through different paths and you want to make sure you have coherency and serialization. You do the RDMA, you do direct paths. You don't want to put any switching in between because anytime you put any intermediate layer like a network switch or a PCIe switch, now you possibly have a temporary congestion point or head of the line blocking. And you did all of this and you got everything great. And you put it in a big cluster and now tail latency start biting you. Because doesn't matter how good your network, there's always one packet going to be dropped and one fiber going to flip and one switch got software update in between. And 2 packets arrived in the same place and one of them got delayed. And this tail latency is the larger the scale, the more the tail latency is actually the dominant factor in how fast you can train. And we're seeing GPUs and Trainiums at very, very large scale. Let me talk about GPUs because Trainiums are better. At very, very large scale, you are lucky and you're going to get award if you get your GPU to be 30% efficient. Yeah, probably going to get promoted too, because so many things in the system stall you from, especially this tail latency at scale. Yeah, and the biggest problem with tail latency at scale is obviously congestion and the network protocol. Rocky, whether it's TCP, Rocky, or InfiniBand, they all put them in the same bucket of bad protocols from that. What we did, we created something called Scalable Reliable Datagram. Scalable Reliable Datagram is a custom network protocol that we built. That does dynamic multipathing based on queuing and latency in the network. Retries in microseconds. We expect acts in microseconds. We don't see, we retry on different path. We embrace out of order. We don't want to force order. Actually, we want to do out of order. As long as we can synchronize at the end, let out of order, let the packet flow. Don't delay anything. It's connectionless, so we can scale to thousands and tens of thousands and hundreds of thousands of nodes. And everything runs on Nitro, the same product I mentioned in the first slide. Okay. I'm going to skip this. Okay. So I'm moving now. We talked about the chips because the network. We talked about how we communicate, how we created a communication protocol, a connectionless transport protocol between them. Let me talk a little bit about the compiler. That this part of the compiler is very close to our heart because it goes back to this is where we want to make it as easy, as boring to the users to use our products. In a high level, this is our stack. As a user, you start either from JAX. Very few users use JAX, but they are big. Okay, and most researchers use PyTorch with Dynamo, and you got I think you get the talk from Ping and Jason, and everything goes for us into something called XLA or OpenXLA. Is the high-level optimizer that today Google use for TPUs, we use, and many other people who are building their own network stack use. And below it goes the neuron compiler. So we have people working in all of these and a lot of research opportunities, by the way, on this stuff. Now let me go into what the neuron compiler does. And before to do that, just to be clear, the interface between XLA to the compiler is a stable HLO. That is like your operating system API. This is the API. This is the operators that everybody have to stick with. This is the IR between the open source world and what we do. In the compiler, remember we start with an HLO and we get the graph. And we go through the graph optimization, remove the node, mix the nodes. Then we do loop optimization. Then we reorder the loops, especially when you do a lot of matrix multiplications on your name. You reorder the loops in such a way that 2 or 3 inner loops can translate into a native CISC instruction. And then we go to the scheduling and allocation, where we remember ordering and try to squeeze as much time as possible. Pipelining and hiding latency. Now, this is all good, but most people want to innovate. They want to create their stuff. They want to create their own code. To create your own code, whether you're a student or a performance engineer or a scientist, I'm disclosing this because we haven't publicly shared it, but I think next month it's going to be made public. There's something called neuron kernel interface, which is a language for you to almost bypass all the layers of the stack and go build optimized kernels at the tile level. So XLA or torch.compile will break the graph, and now you get an instruction to the tile level instruction. And here where you can start optimizing, whether it's attention or give you examples. First of all, this is where Nikki, the kernel interface fits. You bypass all that stack. And things you can implement, like, for example, transpose, you can then tensor attention, you can do fuse softmax, fuse layer norm with fused attention. All of these things you can optimize. And now here's the beauty. People optimize CUDA for 30 years. Systolic arrays, vector engines, the stuff we have are new things. And there's so much room to innovate. And that's why I think a lot of the people come to work for us, they love this because it's not something you took a class in and studied and everybody did the same homework already 10 times. Now, when we have Nikki, I think a lot of you guys attended the PyTorch or PyTorch 2 compiler talk. In aligning with them, I don't know if they use the word compiler or inductor. Did they use inductor? They used inductor, good, okay. One of the ways we think that we're going to support and the industry going to adopt, hopefully the industry going to adopt, and we're funding a lot of research, a lot of projects, hiring a lot of people to work on this one, is to enable PyTorch 2.0 with an inductor, with a backend. Same the way they have a backend to Triton, we'll have backend to Nikki, to our bare metal kernels. We love this because now this entire purple stack is open source. I want as much of my stack to be open source, but in a structured and well-architected open source. And this is the first time we see an outside XLA. This is the PyTorch inductor and Dynamo is really the first time we see a very well thought through open source stack. And I think it's a lot of research and innovation can come on this side. Okay. You guys trust me, we have very good compiler profilers. Like this is, you can do LS and you see all the topology. You can do top and you see the cores. So everything you're familiar with without, if you know how to run on a Linux shell, you'd likely know how to run on our products. This is a profilers I'll skip. This is, for example, how we tweak Llama. Okay, how you can get involved with the stuff we have. First of all, the barcode, sign it up, research opportunities, internships, full-time jobs. So after you graduate, you have to graduate first, of course, and make your professor happy. You can get involved with all the open source projects, inductors, JAX, OpenXLA. Nikki, the kernel development next month going to be available. A lot of rooms for innovation. We're probably going to may do competition and some awards for optimizing kernels, research, summer internship, and we're looking for PhD doers. So finish the PhD and come become a PhD doer when you're joining us. Okay, and thank you.
Plenty of time for questions, so step ahead, state your name and affiliation, and keep going.
Hi, this is Simone Campanoni from Northwestern University. Thank you for the great talk. I can see all of you are having a great time and fun and playing with all the things.
I told you.
So the hardware is, I assume, like it's going to keep evolving and you're going to improve it. So in some sense, it's a moving target for the compiler. And I wonder, like, if the compiler is evolving fast enough to catch up with the evolution of the hardware, and if it is not, is there a plan to make the compiler evolving faster, other than hiring more people?
Okay, so it's a good question. So a couple of things. One, the hardware is move fast. We are between us and NVIDIA, probably the fastest moving people on hardware. However, the ISA is not. The ISA is not moving fast. And usually compiler you design for ISA. When hardware move fast, I would say usually from generation to generation, 80–90% of the work is speeds and feeds. The next fastest interconnect, the next process to do more, faster compute, the next faster memory. We do tweak things, some things in hardware, like we add a new FP7. I don't know, just example, okay? But the hardware doesn't change that much that requires rethinking on the compiler. Now, is the compiler moving fast enough? No, I'm never happy with any compiler, okay? And partially because we get new chips every 18 months, and that's a record in this industry. We execute, and every chip from first generation goes to production, first silicon.
So is there any plan to make the compiler evolving faster?
Yeah, open source.
Okay, got it.
Open source, inductor, PySource 2, Nikki. Let's go.
Thank you.
Hi, I'm Roshan Dattatreya from Microsoft Research. Thank you for a good talk.
I'm Sar.
Yes.
Sorry to hear that.
So I want,
just
can
kidding.
you share more details about the ISA itself? If I understand right, it
The
looks
what?
like the ISA itself.
We're gonna make it public next week, next month.
Cool.
They're gonna be Nikki.isa, and you just see the ISA itself.
But Nikki is a intermediate language, like
It's
right?
almost the CISC instructions.
Okay.
It's almost
Cool.
the same.
Okay, thank you.
You're welcome.
Thank you for your insightful talk. This is Devesh Tiwari from Northeastern, and thank you for reinforcing that simple names actually do matter, and Trainium 3 should come after Trainium 2. At some point in your slide, you said high performance per carbon footprint. I'm curious to know, are there architectural innovations or optimizations that we have learned traditionally that you had to throw away or employ them or continue employing them as you thought about carbon footprint of your devices?
So it's an excellent question about carbon footprint. And this is the typical mistake everybody does. People today go, especially when you buy CPUs, oh, I have the lowest power per performance. That is the wrong metric, because when you buy a chip or you build a chip and you build the server, before you turn it on, you will likely spend more than 50% of the carbon footprint of that chip building the chip, building a PCB, building the memory, building the rack, building the. So when we look at the minimizing carbon footprint for the lifetime of a product, usually that doesn't drive lowest performance per watt. Actually, sometimes we burn a little bit more power. We get into the least efficient curve, because with the more performance, I need to use less chips.
Thank you. How do you accurately evaluate all those? Or how could
We have
the
models.
how could community actually contribute towards that? One of the challenges is in carbon footprint is accurate modeling of the things.
Yeah, luckily we're Amazon. We get a lot of data, and there's a lot of people who are refusing to give data, and it's not good for the environment. It's not good for research, and we're doing everything we can try to push people to publish it and we give data.
And did you say that that was also going to be open source next month?
I hope so.
Okay.
Not in our control. Whatever in our control, we do. This is what we call a category 3. And you know, Amazon have the climate pledge. Amazon, one of the greenest companies in the world, and we're using our buying power to get our vendors to open up their books and their data, because we need to report that data to our constituents.
Thank you. Very helpful.
Hi, thanks for the great talk. My name is Deep Maiti. I'm a performance engineer at Zoox. It's another subsidiary of Amazon. I have a question about, like, is there any plans for Annapurna to compare and benchmark against the other ML common with the ML Commons community so that we see how it's performing?
Absolutely not.
I see.
Because I don't. Yes, you're a customer. Bring your credit card. In $2, you can run whatever your specific workload on Amazon, on Trainium. Another $2, you can run your workload in GPU. And based on your workload, you decide. ML Commons is like spec end. It's never been good. Okay?
Thanks.
But that's beauty of the cloud. With a small credit card, you can experiment, run your workloads. So in principle, we refuse to publish spec ends the same way we refuse to publish ML Commons. And we think that's a misleading data. You guys agree, right? I guess. Thank you. Thank you.
Hi, Anton from Edinburgh. I was wondering if you said you look at the carbon footprint, but you have like a new chip every 18 months.
Mm-hmm.
Have you considered lengthening that period in order to reduce the carbon footprint?
I'll tell you why. First of all, you should ask me, why do you have a new chip every 18 months? Okay. Because the new chips every 18 months, because usually every 18 months, there's a new silicon process, and then there's a new silicon process and a new HBM, faster HBMs. And when we do all the numbers, that speed we gain, every generation, typically we gain 2 to 3x performance. Yes, we pay a big carbon footprint, but when you're getting 3x performance is on the net in the integral, it's much less. Now, if you're doing a CPU, let's say, and you know, best case in CPU, you're going to get every generation to generation 10, 15, 20% if you're lucky. You're a regular CPU. There we do that consideration. And actually our CPUs, for example, Graviton, we do it every 2 years to 2.5 years because of that consideration. We don't do it every 18 months. Because everybody's getting in a CPU to the plateau area where the increment is small.
All right, thank you.
Hi, great talk. I'm Anish Saxena from Georgia Tech. I'm a PhD student. So you clearly have embraced CISC architecture. So
no, only for Trainium. My Graviton is all RISC.
Right? So one of the issues that Intel faced when they doubled down back in the day was that things went out of favor, but you still had to support it because when customers kept using it.
What does out of favor mean?
Some instructions.
People stop writing papers about it to say how bad it is, right? Okay.
Or there were let's say you have a newer model which uses a different kind of way to do things. And then what instructions you currently have are not the most optimized, but people still use them. So how do you expect to not have the architecture bloated over time with instructions that customers might stick to, even though that's not the most optimal thing?
I don't think we're going to have a, so first of all, we have to keep compatibility.
Yes.
And we are still in a stage where instruction set is so small. I don't mind it get doubled or tripled or quadrupled. Okay. It's a valid problem, but I don't think it's a CISC specific problem. You could have the same problem with RISC.
Mm-hmm. Makes sense.
Okay. So again, I think Intel CISC for CPUs is bad because every instruction is one cycle and instruction size and the data size are so close to each other.
Right.
Here, I don't, every instruction is 1,000 cycles. I can afford bloated instructions.
Makes sense. Thank you.
Joseph Torellas from Illinois. I think you implied you would tell us more about sparsity. How do you support it and what are future plans?
I will. In
this talk.
So did I imply that?
I thought there was a question before. It said.
No, the question said how we do it. Yeah, but there were. I will have to give you NDA, but we're gonna make it public soon. Okay.
All right.
But let's say it will be a very useful way of structure sparsity. We can take offline if you don't mind.
If nobody understands the gap, I can ask the last question. So it's great that you're open sourcing the NKI and the compiler, and people can do amazing compiler work. What about the people interested on the hardware side, the network, the system software, scheduling, and this kind of thing at a bigger level? What do you see the top few challenges that you would like people to start tackling? Whether they can do it easily, or infrastructure, no, it doesn't matter. But what do you think are good topics for all these young PhDs here to consider in this space?
So I think if you're in networking or distributed systems, the area of distributed training, collectives, all the stuff being done in MPI for the last 20 years have to be revamped. Rewritten, the algorithm be rethought for this ML. And this is one of the most underserved and under research area. And I see that because I hire a new engineer and tell him, go look at this problem, and I come back, he gave me 2x performance. That means, it's not like he's the most genius in the world. It's just the area has been underserved. Okay, so there's a lot of research. There's a lot of research in that area, and that's research both in the algorithms as well as in the network protocols itself.
Any more questions? All right, let's thank Nafea.
Thank you. What? Perfect on time. I skipped all the slides. I wanted to give time to skip the questions. So, no, but no, we're not exposing the microcode. But if you sparsity is the instructions. You like it? You like it?